Welcome back to our channel. Today we will differentiate logarithmic functions. We start with the natural logarithm, that is ln x, prove its derivative from first principles, extend to logs with other bases, and then use logarithmic differentiation to handle difficult expressions like x to the power x. So first of all, we are going to start with the function ln x. We'll call that example 1 as always. And what does example 1 state? Differentiate ln of x. So first of all, we need to know that we are going to prove this differentiation or this differential using the first principle. But in order to do that, we first have to recall our formula for the first principle. So what does the first principle state? It states that the derivative with respect to x of a function f of x is equal to the limit as h tends to 0 of f of x plus h minus f of x all divided by h. But in our case, what is f of x? So we then first of all let our f of x be the function ln x. After letting our f of x be the function in x, we then need to calculate the function f of x plus h. F of x plus h is then equal to the function ln of x plus h. After calculating this, we then need to calculate our numerator, which is f of x plus h minus f of x. F of x plus h minus f of x is equal to ln of x plus h minus ln of x. And if we recall from our logarithm principles, we know that the ln of x plus h minus ln of x is the same thing as ln of x plus h, all that divided by x. Simplifying this further, we obtain ln of x on x plus h on x, which simplifies to ln of 1 plus h on x. Now we then need to divide by our denominator h. F of x plus h minus f of x all divided by h gives us the function ln of 1 plus h on x all divided by h. What are we going to do then? We are going to divide the numerator by x and the denominator also by x. Why are we performing divisions on both the numerator and the denominator? This is to avoid any change to our initial equation. If I divided just the numerator by x, I will have a change to my initial equation, which will cause problems in my solution. So in order to cancel out this change, I need to perform the same operation on the denominator. So performing this operation, we have ln of 1 plus h on x all divided by x and h divided by x. Now carrying this x to the other side, we have this is nothing. We have 1 on x into ln of 1 plus h on x all divided by h on x. So what are we going to do? We will say let k be equal to h on x. And what do we observe? We observe that the limit as h tends to 0 of h on x is equal to 0. So this implies that the limit. So what can we then conclude from this? We can then conclude that the limit as h tends to 0 of our function 1 on x times ln of 1 plus h on x divided by h on x is same thing as the limit as k tends to 0 of the function 1 on x into ln of 1 plus k on k. It might seem a little bit odd or doesn't actually make sense, but what we just did is correct. Let me re-explain this again. in order for you guys to understand perfectly well. We are having the term here h on x, and we want to reduce this to a simple constant k. We observe, we know, first of all, we let k to be the ratio h on x. Now observing, since we are calculating the limit as h tends to 0, we want to observe how k behaves when h tends to 0. And what do we notice? We notice that as h tends to 0, k also tends to 0. So that tells us that the limit as h tends to 0 is same thing as the limit as k tends to 0. So that is what we did in this case. The limit as h tends to 0 of this term is same thing as the limit as tends to 0 of this term where h on x is replaced by the constant k. So simplifying this further, this can still be equal to 1 on x times the limit 1 on x times the limit as k tends to 0 of the term ln of 1 plus k, all that divided by k. Now, what do you need to know? You need to observe, or you need to memorize that the limit as k tends to 0 of the term ln 1 plus k on k is a standard limit which equals to 1. What does this then simplify to? This simplifies to 1 on x times 1, which implies that our function, the limit as h tends to 0 of f of x plus h minus f of x divided by h, which was same thing as the derivative with respect to x of our function ln x, is equal to 1 on x times 1, which equals 1 on x. So what can we then conclude? We can then conclude that therefore the derivative with respect to x of ln x equals 1 on x. We enclose our answer. Now let's move on to the second case of log x. We'll call this example 2. What does the example states? Differentiate log x. What is the first thing we're going to do? Here let's put log to the base a, that is for any base, log to the base a of x. What's the first thing we're going to do? We're going to perform, the first thing we're going to do is let first of all our f of x be equal to log x, log to the base a of x. That is, let f of x be equal to log to the base a of x. Now we are going to perform a change of variables, that is changing our change of basis, sorry, that is changing our base to the base e. This implies that f of x, which is equal to log of x a, is same thing as log of x e on log of a e. And we know that log to the base e is same thing as the natural log e, so the natural log ln, so this simplifies to ln x on ln a. Now calculating the derivative of this term, the derivative with respect to x of the term ln x on ln a is same thing as 1 on ln a times the derivative with respect to x of ln x. In this case, we remove the term 1 on ln a because this is considered as a constant, as it doesn't depend on our variable, our differentiation variable x. So in this case, we can remove it out, which was the constant multiple law. From our first example, we know that the differential with respect to x of ln x gives us 1 on x. So this tells us that the differential of our function f of x in this case gives us 1 on ln a times 1 on x, which then simplifies to 1 on x ln a. So what can we then conclude from this? Therefore, the derivative with respect to x of any logarithmic function of the form log to the base a of x gives us 1 on x ln a. Perfect. So let's move on to a third example. In this example, we are going to calculate for a general type of function, that is ln of g of x. So example 3. And what does the example state? Differentiate ln of g of x. So the first thing we're going to do is let f of x be equal to ln of g of x. So this is same thing as a function of a function. And what does that tell us? That tells us that to differentiate this, we need to apply the chain rule. And applying the chain rule, first of all, asks us to identify our outer and inner function. So first of all, what's our outer function? We'll say let our outer function in this case is ln of x, and our inner function in this case is g of x. So what we're calling from our chain rule, which says that the derivative with respect to x of, this time let's use a function h of g of x, is equal to h prime of g of x times g prime of x. So first of all, we're going to calculate h prime of g of x. In this case, h is our outer function and g of x is our inner function. So what is h prime of g of x? H prime of g of x, in our case, which is h prime of g of x, let's use u. First of all, h of x, h of u is our outer function, ln of u, outer function. This implies that h prime of u gives us the function 1 on u. Now identify our inner function. G of x is our inner function. So let u be equal to g of x implies that h prime of g of x is equal to 1 on g of x. Now from our chain rule, the derivative with respect to x of f of x in our case, which is, this implies that d on dx of f of x, which is equal to d with respect to x of ln of g of x, is equal to h prime gx, that is 1 on g of x, times g prime of x. So what can we then conclude? Therefore, the derivative with respect to x of the function ln of another function g of x is equal to g prime of x on g of x. We box our answers. So for our last exercise, we are going to solve the question. Let me give, this one is a practical example, a practical exercise. Practical exercise 1. And what does the question tell us to do? Differentiate the function x to the power x, y equal to this. So I'm going to solve this throughout with you guys. Just follow up, keen, and be attentive in order not to miss a single step. So what's the first thing we're going to do? We're going to apply ln on both sides. That is ln y equal to ln of x to the power x. What does this give us? Ln of y equal to x ln x. Now, applying the base e on both sides, we have e to the power ln y equal to e to the power x ln x, but this gives us y. This implies that y is equal to e to the x ln x. Now, if we recall, the derivative with respect to x of a function e to the g of x is simply equal to g prime of x e to the g of x, if we can recall very well. So first of all, we're going to calculate g prime of x. First of all, we have to calculate g prime of x. So first of all, we'll let g of x be equal to x ln x. How do we now calculate g prime of x? The first thing you notice is that this is a product of two functions. The first function is x and the second function is ln x. And if we recall our product, what does our product hold state? Our product hold states that the differential of this term is this times the differential of this plus this times the differential of this. So this implies that g prime of x is equal to x times the differential with respect to x of ln x plus ln x times the differential with respect to x of x. This gives us x. What is the differential of ln x? The differential of ln x is 1 on x plus ln x. And what is the differential of x? 1, which gives us 1 plus ln x. Now, applying this directly to our solution, the derivative of, with respect to x, of e to the x ln x is equal to g prime of x 1 plus ln x times e to the g of x e to the ln x. So what can we then conclude? Therefore, the derivative with respect to x of our term x to the power x, which is still the same thing as the derivative with respect to x of the term e to the x ln x, is equal to 1 plus ln x times e x ln x. We box our answers. So in the next video, we'll combine exponentials and logarithms in more advanced differentiation and also prepare for the product, quotient, and chain rules in full generality. Thank you guys, and expecting you in the next video. Bye.